This is section 5.1, Trigonometric Identities. The I can statements for this section: I can identify and use trigonometric identities to find trigonometric values, and I can use basic trigonometric identities to simplify and rewrite trigonometric expressions. An identity is an equation where the left side equals the right side for all values of the variable for which both sides are defined. So this means it doesn't matter what value you put in for x, the left side will always equal the right side if it's an identity. A trigonometric identity is an identity that involves a trigonometric function. So we learned about our trigonometric functions in chapter 4. On this part, we're going to talk about the reciprocal and the quotient identities. Remember, the sine of theta is equivalent to 1 over the cosecant of theta. Cosine of theta is equal to 1 over the secant of theta, and tangent of theta is equal to 1 over cotangent of theta. We can do the same thing backwards, so cosecant is just 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. The quotient identities, the tangent of theta can be rewritten as the sine of theta over the cosine of theta, and cotangent, because it's the reciprocal of tangent, is just cosine over sine. So for this example, we need to find the sine of theta if we know the cosecant of theta. Remember, the sine is the reciprocal of cosecant. So if you know the cosecant, to find the sine, you just find the reciprocal, which means you just take the fraction and flip it. So we end up with sine of theta is equal to 4 over 7. If we need to find the cosine, if we are given the cotangent and the sine, remember cotangent is just equal to cosine over sine. So we can fill in the values that we know. Our cotangent is 2 over 5 radical 5. Our cosine is unknown, so we're just going to leave that as cosine of theta. And our sine value is radical 5 over 3. Now we want to get that cosine of theta by itself. Right now we have cosine divided by radical 5 over 3. The opposite of dividing is multiplying, so we are going to multiply both sides by radical 5 over 3. Now we have a radical 5 on top and a radical 5 on bottom, so those can cancel. And we're left with the cosine of theta is equal to 2 over 3 times 5 is 15. So cosine of theta is equal to 2 over 15. The trigonometric functions can be defined on the unit circle. We can apply the Pythagorean theorem to this right triangle to establish another basic trigonometric identity. If we look, remember on Pythagorean theorem, a squared plus b squared is equal to c squared. Or in this case, x squared plus y squared is equal to 1 squared. But remember, your x value is actually cosine, so we can say cosine of x squared plus sine of x squared is equal to 1. When you square a trig function, you can actually write it as cosine squared of x plus sine squared of x is equal to 1. Or we can rewrite that as the sine squared of x plus the cosine squared of x is equal to 1. This is actually one of our Pythagorean identities that we're going to have on the next slide. So there are 3 different Pythagorean identities. We have sine squared plus cosine squared is equal to 1. We could also go back, use that same unit circle, and use our triangle to show that tangent squared plus 1 is equal to secant squared. And we can show that cotangent squared plus 1 is equal to cosecant squared. The important thing here to notice is that sine squared of theta is equal to the sine of theta squared. It's just a different notation to make it a little bit easier for us to write. So if the tangent of theta is equal to -8, and we know that the sine of theta is greater than 0, we need to find sine and cosine. Now if we only have one value, and it has two different parts, tangent is sine over cosine or it is y over x, we can't just separate it and say which piece is which. We don't automatically know that sine is going to be an 8 and cosine is going to be a 1. There could be a lot of different values. So we are going to have to use one of our Pythagorean identities. So if we come back and look at these, our Pythagorean identity that deals with tangent is that tangent squared plus 1 is equal to secant squared. So we know what our tangent value is. Remember, you can just write that as tangent squared. Negative 8 squared is going to give us 64. 64 plus 1 gives us 65. To get rid of that square, we are going to take the square root of both sides. Remember, when you take the square root, it is positive or negative. So we know that the secant of theta is either equal to plus or minus radical 65. Now we need to remember that tangent is sine over cosine. Our tangent value is negative, so that means either our numerator had to have been negative or our denominator had to be negative. They tell us that the sine has to be positive, so that means our cosine is negative. Now if you remember, secant is the reciprocal of cosine, and if cosine has to be negative, that means our secant also has to be negative. To find our cosine value, we just take our secant and we flip it upside down. So it'd be 1 over negative radical 65. But we're not allowed to leave radicals in the denominator, so we'll move that radical to the top and leave the number on the bottom. So the cosine of theta is equal to negative radical 65 over 65. Now again, we need to remember that tangent is sine over cosine. We know our tangent value is negative 8. We don't know what our sine value is, but we just found that cosine is negative radical 65 over 65. Right now we have sine divided by our value. So to get the sine by itself, we do need to multiply both sides by negative radical 65 over 65. So we are going to get that the sine of theta is equal to negative and negative is going to make that positive. So we're going to have 8 radical 65 over 65. If we could reduce that any, you can go ahead and reduce. This one is non-reducible. A trigonometric function f is a cofunction of another trigonometric function g. If f of alpha is equal to g of beta, where alpha and beta are complementary angles. So what this is saying is if we have two complementary angles, it's the two acute angles in a right triangle, the sine of alpha, remember sine is opposite over hypotenuse. So our opposite side for alpha is y, our hypotenuse is r. This is going to equal the cosine of our beta and cosine is adjacent over hypotenuse. If I'm looking at my beta, the adjacent side will be my y, my hypotenuse will be r. So we notice that the sine of alpha will always equal the cosine of beta. Another way to write that is that your beta value inside a triangle, we have 180 degrees. We've already used 90 on this angle, so you're left with 90. And then if you subtract the alpha, you should get your beta. So another way to write the beta is to say 90 minus alpha. So we know that sine of alpha is equal to the cosine of 90 minus alpha. Same thing with tangent and secant. Tangent of alpha is going to be cotangent of 90 minus alpha. Secant of alpha is cosecant of 90 minus alpha. Now, instead of 90 degrees, we can write this in radians. Remember, 90 degrees in radians is pi over 2. So this gives us our cofunction identities. We know that the sine of theta is equal to the cosine of 90 minus theta, or pi over 2 minus theta. And we can have the same thing for all of these. Now, when we're looking at the unit circle, remember there's positive and negative values. So when we're looking at the right side of our unit circle, the sine of alpha, sine, remember, is your y value, would give us a positive y. The sine of negative alpha is going to take us down here. That would have a value of negative y. So if I plug in a negative alpha and it gives me a negative value, that means it is an odd function. So cosine is an odd function. Sorry, sine is an odd function. Cosine is your x value. If I put in the cosine of alpha, that's going to give me x. But we're on the right side of the circle, so if we did the cosine of negative alpha, you're still on the right half of your unit circle. So our x value is still positive. So if you plug in a negative alpha and you still get out a positive value, then you have an even function. So that means cosine is an even function. So our odd and even functions, sine, cosecant, tangent, and cotangent are all odd functions because anything that has a sine involved in it will be odd. Cosecant is just the reciprocal. Tangent is sine over cosine, so it has a sine, and cotangent is cosine over sine. The only two even functions are cosine and secant. Now we know that the tangent of theta is equal to 1.28. We need to find the cotangent of theta minus pi over 2. Now if we look back at our cofunction identities, we know that the tangent of theta is actually equal to the cotangent times cotangent of pi over 2 minus theta. When we look here, we need to find the cotangent of theta minus pi over 2. That's not in the same order. We know that tangent is cotangent of pi over 2 minus theta. Now the only way I can change these signs and to rearrange them is if I factor out a negative 1 out of both pieces. So if I factor out a negative 1, theta divided by negative 1 gives me negative theta. Negative pi over 2 divided by negative 1 gives me a positive pi over 2. Since this is just addition and subtraction, you are allowed to rearrange the order. So negative cotangent of pi over 2 minus theta would equal a negative tangent of theta, because this is negative. We plug this over in here. A negative cotangent of pi over 2 minus theta will equal a negative tangent of theta. Since we're just looking at to find the negative version of my tangent, because tangent is an odd function, when you look for the negative value of it, it is just going to be the negative tangent value. So if we need to find the cotangent of theta minus pi over 2, this is equivalent, remember, to the negative tangent. Since tangent is an odd function, when you make it negative, when you put in a negative here, it just is going to come out as a negative here. So cotangent of theta minus pi over 2 will just be a negative 1.28.